Okay. Yeah. Start. Okay, so good evening. So sorry for the late. So uh, let us start today interaction. So if you have any questions, so you can write. So if you have any questions, so you can write and I will be able to answer. So otherwise we can start the discussion regarding the assignments what I have given. So last class we have, or last interaction meeting, so we have discussed up to assignment number 3. So now we will discuss the assignment 4 to 7, 4, 5, 6. Today we will discuss 4, 5, 6, and on 5th we are going to discuss the remaining 7, 8, 9 and 10. So these 4 things we will discuss on 5th April. Okay, so you can show the slides. So if you have any questions, so now you can ask. Not this one, so that where it's written assignment 4, so you have seen that. Go 35%. Next, from here. So actually in this up to 3 you have seen. So now in assignment 4, so particularly we have discussed regarding different methods, perturbation methods we have discussed. So perturbation methods, you know, so there are several perturbation methods. For example, Lindstedt-Poincare technique, then method of averaging. So in method of averaging also, so you have studied this KB method, Krylov-Bogolyov method, Krylov-Bogolyov Metropolsky method, and this van der Poel's method. So then also you have studied regarding this method of multiple scales. Then combining this method of multiple scale and harmonic balance of methods are there, which I have asked you in this assignment. So though I have not taught you, so I told you to read those things, these advanced things. And so let us now discuss regarding this assignment. So where the first question is, in method of multiple scales, taking epsilon equal to 0.1, so what is T4 by T? So that thing you have to answer. So that is, so you know your Tn equal to epsilon to the power nt. So T is the time, so we are taking different time scales like T0, T1, T2, T3, like that we are going to take. So here this T0 equal to epsilon to the power 0 T, so that is equal to T itself. Then this T1 equal to epsilon to the power 1 T, that is epsilon T. Then T2 equal to epsilon square T, that is so epsilon square T. Then T3 equal to epsilon cube T. So this way you got different time scales. So here in these questions it has been asked, that is T4 by T. So T4 will be equal to, so epsilon to the power 4 T by T. So this will be equal to your epsilon to the power 4. So here epsilon is given to be 0.1. So this will be equal to 0.1 to the power 4. That is 1 by 10 to the power 4. So then it becomes 1 by 10 to the power 4, or it is 10 to the power minus 4. So this way you can find the relation between T4 and T. So here it is 10 to the power minus 4. I hope you understood this thing. Similarly, so these are the different time scales, like the second hand, minute hand and the hour hand we are using. Similarly, these are different time scales used to show how the slowly varying and with a rapidly varying times, and by using different time scales you can solve these problems. Next question. So in the second question it has been asked, for the governing equation x double dot plus 2x plus 0.02 x dot plus 0.04 x cube equal to 0.5 cos omega t, to have the effect of nonlinearity one should at least go for the time scale. So up to what time scales you can go, so it has been asked. So you just see see the nonlinearity. So your linear part, so in the linear part, so the coefficient of x, you just see the coefficient of x is 2. and in the nonlinear term, so you have the coefficient of xq that is equal to 0.04. So the coefficient of xq equal to 0.04 and this is equal to 2. So if you are taking for example epsilon equal to 0.1, so then this thing can be written as this is 0.1, so 0.1 square into 4. So 0.1 square equal to 0.01, so into 4, so that becomes 0.04. So that means your nonlinearity is of the order of epsilon square. So you are taking a nonlinear term of the order of epsilon square, that is you are taking epsilon square x cube. So as you are taking, this is of the order of epsilon square x cube. So x cube is written of the order of epsilon square. So you can go up to T2 to solve these problems. So next question. So while eliminating the secular term using method of multiple scale, following equations are obtained. So you just see what is the equations you got. So that is d1a equal to 3a square plus 2a bar, and d2a equal to a square a bar plus a bar square plus 2a cube. Using dA equal to, so you can use this thing, dA by dt equal to epsilon d by dt1. So d by dt1 is nothing but your d1. So then plus epsilon square d by dt2, that is d2, and a equal to half a to the power a e to the power I beta. Which of the following statement is correct? So you can substitute this equation in the equation d1a and d2a, and substitute this a equal to half a to the power half a e to the power I beta. Then you can write down this equation. So the equations, you can get a equation in terms of a dot and gamma dot. So I hope you have done this thing. So if you do this thing, so from this thing you can see, so in the a dot equation you can have a term a into something. Similarly here in the gamma equation also you will get. So here you can clearly observe for steady state, this a and gamma will not be function of time. So as a and gamma are not function of time, so this a dot equal to 0 and gamma dot equal to 0. So as a dot equal to 0 and gamma dot equal to 0, so if you have a term a multiply with something equal to 0, so a must be equal to 0. So a is 0 is the trivial state. A equal to 0 is the trivial state solution. So this is the trivial state solution. Okay. So here, so by solving this thing or by doing this thing, so you can check that the system has a trivial response. So you will get a term like this, and from this thing, so you can verify that the system has a trivial state. So other options will not be there. Okay, so you can verify that one, and from this thing you can see, for example, the system is subjected to periodic excitation. So here where is the forcing term? So you don't have a forcing term exclusively in this equation. So from that thing, so you can tell that, so this is not correct one. Similarly, this cubic term, the system has only cubic nonlinearity. So you just see the system has, so you have a term a bar. So the system has a quadratic nonlinearity also. A cube is there, so the system has a cubic nonlinearity. So as the system has both cubic and quadratic, so this option is also not correct. So similarly, the system has no trivial response. So by solving these things, so you can verify that the system has a trivial response. Okay. So next slide. Okay. So let us see the next question. For the equation u double dot plus u plus epsilon alpha u cube equal to 1.2 cos omega t using method of multiple scale, by taking u equal to u0 plus epsilon u1 plus epsilon square u2, u0 can be written. So you just see here what is happening. So in the right hand side, the forcing term, so we are not using any epsilon. So you just see the coefficient of u is 1, and also the coefficient of the forcing term, that is 1.2 cos omega t, so that is 1.2. so they are comparable. This is 1 and this is 1.2, so they are comparable. So here the coefficient is 1 and here the coefficient is 1.2. So as they are comparable, so it is not of the order of epsilon. So here you have a strong forcing term. So the forcing is strong in this case, it is not weak forcing. So as you have a strong forcing term, so in that case, that in the first equation itself, so you will have this u term. So the equation you will have d0 square u0 plus u0 will be equal to, so that term will be there, that is 1.2 cos omega t. So this cos omega t you can write in terms of, for example, this cos omega t you can write e to the power I omega t plus e to the power minus I omega t by 2. So from here, so you will have half e to the power I omega t plus half e to the power minus I omega t. So this plus cc you can write, this is complex conjugate of this thing, and substituting this in terms of this cos omega t, so you can have 1.2 by 2 e to the power I omega t. So the particular integral will contain, so the complementary part, so when this right hand side equal to 0, so for that thing you can get a e to the power I t plus a bar e to the power minus it. So the complex conjugate part you need not have to write. So the solution will contain a e to the power it plus for this part, so for this part we can have, so here also, okay, so here also you should have cc. So you just see in the first part cc is not written, so that is not the correct answer, that's why. So in the second thing, e to the power a e to the power minus it plus 0.61 minus omega square e to the power minus omega t. So this is due to the strong forcing part you are getting, and this part you are getting from the complementary function, that is a e to the power minus it, and then the cc, that is complex conjugate you will get. So that's why these two terms you will get. So normally if it is of the order of epsilon, then this term will not be in the first equation. In the first equation itself you will get right hand side equal to 0, and your solution will be u0 equal to a e to the power minus it plus a bar e to the power it. So that part will go in cc, that is complex conjugate. So I hope you understand this thing, and you must have made a lot of practice by using this method of multiple scales, and you have solved more problems on this thing. So you most probably you know this thing, and if you have some doubt, then you can write back to me now. Okay, so the fifth question. So for the equation x double dot plus x plus 0.1 x dot equal to 0.1 cos omega t, taking epsilon equal to 0.1 and x equal to x0 plus epsilon x1 plus epsilon square x2 and tn equal to epsilon nt, x0 can be written as. So you know this thing. So here you just see whether it is which one is the correct answer. So in this case you just see, so first you have to order the equation. So in this case the equation is written x double dot plus x plus 0.1 x dot equal to 0.1 cos omega t. So here epsilon is given, you have been given the hints that epsilon equal to 0.1. So you can write this equation in this form, that is x double dot plus x plus epsilon x dot equal to epsilon cos omega t. So here, so this is you have a weak forcing term here. So as you have the weak forcing term, it is of the order of epsilon. So in the first equation, that is the order of epsilon to the power 0. So this term will not be there. So your equation will be d0 square u0. Okay, d0 square. So it is written in terms of x. So you can write d0 square x0 plus x0 will be equal to 0. So this complementary part will be only there, so that you can have the solution x0 will be equal to a e to the power I t0. So here you just see what is a is a constant with respect to your t0. So as it is d0, so it is a constant with respect to t0. So that's why it is written a is a function of t1. So it can be t1, t2, t3, but it will not be a function of t0. E to the power I T0 plus or e to the power I capital T0 you write or small t you write. So it is up to you, and plus its complex conjugate. So this way it can be written. So this is the correct option. That's why. So next question. Okay, so in method of averaging, while solving the equation x double dot plus 4x plus 0.01 x dot plus 0.1 x cube equal to 0.1 cos omega t, one may write. So you just see, in case of unlike the method of multiple scale, so where you have the formulation for weak nonlinearity, strong nonlinearity, or strong forcing, weak forcing. So particularly this method of multiple scale is convenient or is more accurate for the system with weakly nonlinear system or weakly forcing system. So but you can use this method of averaging or Lindstedt Poincare method for any type of nonlinear system. So here what is the assumptions in case of method of averaging? So you can recall that in method of averaging, so you can take a solution where in similar to that of a linear system, but in linear system where you have a constant. So in method of averaging, so those constant will be replaced by the term with slowly varying function of time. So that's why, so in this case, so in this question, so while solving the equation x double dot plus 4x, so these are these, so now you just put actually this term, so this term you can put equal to 0 and take only the linear equation. So linear equation is x double dot plus 4x, so its solution equal to, so x double dot plus 4x, this 4 can be written to square and x, so this is omega n square x, that is x double dot plus omega n square x. So the solution will be equal to a sine or cosine, both the things you can write. So a cos, so it will be 2 a cos 2t plus phi, a cos 2t plus phi, where you just see if it is linear, so this a and phi are constant, but in case of the method of averaging, so you are assuming this a and phi are slowly varying function of time. So you can write here, so that's why the option B is correct. So here x equal to a cos 2t plus phi, where a and phi are slowly varying function of time. So the other options you just see, the first option a cos t, it is written t, but actually as you have 4 here, so it must be 2t, not t, that's why it is wrong. So though this option 2t is written, but here what is written, a is slowly varying function of time, but phi is constant, but phi cannot be constant, phi also should be a function of time. So the option B is correct in this case. So using method of averaging, one may write, so you just see already you know this type of equation. So using method of averaging, so you can reaching this similar equation like this, that is a dot equal to epsilon by 2 pi omega 0 integration 0 to 2 pi sine phi into, so you just see, so you have f x and x dot, let you have x and x dot, so you have the equation x double dot plus f x dot equal to 0. So if your equation is in this form, then here what you have to do, so this x you have to replace it by cos phi, so you can replace this by a cos phi, and this x dot can be replaced by minus omega 0 a sin phi. So this way you replace this x by a cos phi and x dot by minus omega 0 a sin phi to get a dot. So you have to just multiply this thing by sin phi and epsilon by 2 pi epsilon 0 and integrate it to obtain to get a dot. And similarly beta dot you can get by putting this minus epsilon to pi epsilon omega 0 a integration 0 to 2 pi. So here you are multiplying by cos phi, and in the a dot equation, so you are multiplying by sin phi. So replacing a by x by a cos phi and x dot by minus omega 0 a sin phi. So this way you can find a dot and beta dot. So this is the hints given to you. So here the question is, using method of averaging, one may write this equation. So for system with u double dot plus u equal to, so this part is actually okay. So the equation is x double dot plus x plus this thing. So you remove this part and this part, you just write the function of x and x dot, you just write this way and you can get the solution. So here fx f you can write this way and okay. So u double dot plus u equal to minus 0.05 for u dot greater than for 0 and u double dot plus u equal to minus 0.05. So this is actually your Coulomb damping. So the problem is that of the Coulomb damping, that is when u dot velocity is less than 0. So if u dot is less than 0, so you have a value of 0.05 and when it is greater than 0, u dot is greater than 0, so this value is minus 0.05. So the question is just reverse of that of the that Coulomb damping type of thing, and so you can get this equation. So now you can by solving this equation for t equal to 20 second, so you can find the solution and you can write a simple code in MATLAB to find this one. This code I have already written and I will send you this code, and so but you can do of your own also and you can find that the result is coming to be 0.0363. Next. So which of the following statements are correct? So okay, so here you just see the difference between the Lindstedt-Poincare method and modified Lindstedt-Poincare method is in the use of form of response frequency omega. So actually I have given you the reference, so you could have most probably might have read this paper also, modified Lindstedt-Poincare method. So this he in 2002, so he has proposed this method. So modified Lindstedt-Poincare method for some strongly nonlinear oscillation. So it was published in International Journal of Nonlinear Mechanics. So here you just see in case of method of multiple scale, so you have expanded your omega, but in case of this modified Lindstedt-Poincare method, so he has proposed to expand this term omega square. So instead of expanding this term epsilon in terms of this bookkeeping parameter, here the term omega square is expanded, and so one find the solution because this omega square term you are using in this. For example, if you take this t equal to or tau equal to omega, so your time you just take, so tau non-dimensional time equal to omega t, omega in radian per second, time in second, so second cancel and this becomes non-dimensional. So then your d square, for example, you write this d square y by d t square, so this will be nothing but, so it will be equal to your omega square d square y by d tau square. So this way you can write, and this omega square term you have to expand. So this omega square term you can write, this is equal to, for example, omega 0 square plus epsilon omega or 0 1 let you take, so 0 2 square plus epsilon square omega 0 3 square. So this way you go on writing, expanding this term of omega square, where this omega 0 1 is only known term, that is the coefficient of your y, so that term is only known, and these other terms has to be found from the condition similar to that of the secular terms, and you can get the method of this Lindstedt-Poincare and modified Lindstedt-Poincare are same, but here you are just expanding this omega square, and in Lindstedt-Poincare method you are expanding omega. So that's why this option is correct. So in method of normal form, so I have written the book, so you might have followed that thing by Nafe method of normal form, there is a book. So one start with a linearized equation and then normalize the remaining term in the simplest form. So the third one, in incremental harmonic balance method, that is IHBM, improved incremental harmonic balance method, that is IIHBM, and alternating frequency time domain AFT method are used for analyzing systems with non-polynomial nonlinearities. One has to pay attention for the sampling rate. So you have to So this paper you can see, so 3 papers so has been given here, so you can see these papers to know more regarding these methods. Okay, so these 3 options were correct. So you can see this fourth option, method of multiple scale cannot be used for system with fractional order nonlinearity, so this is wrong. So you can use this thing also for the fractional order nonlinear system. So we have given a reference also for the fractional order system. So you can see clearly that this method of multiple scale can also be used for the system with fractional order nonlinearity. Okay, so next. So next question, so using method of averaging, one may write A dot equal to, so this is the question already, we have similar questions we have seen. So using method of averaging, so one may write A dot equal to epsilon by 2 pi omega 0 integration 0 to 2 pi sine phi into that f. So in case of f, that x is replaced by a cos phi and omega, so that x dot is replaced by minus omega 0 a sine phi. Similarly, you can write this beta dot equation. So in this case, you just see, so we have given a system with quadratic nonlinearity, quadratic damping actually. So x dot is damping, so x dot is damping, and you are multiplying this mod x dot. So what is mod x dot? So mod x dot is nothing but, so it is equal to x dot if x dot greater than 0 minus x dot if x dot less than 0. So you have two value of x dot. So this equation, so with quadratic nonlinearity, so if you solve this equation for t equal to 20 seconds, so you can find this answer. So you can write your own code. So this is just simple integration, so you can, it is not difficult for you to solve it. I think you can solve it and you can find, and you have already solved this problem. So if you have any doubt, so I'll send you the code, you can verify yourself also. Next. So which of the following statement are correct? So in higher order method of multiple scale, actually this higher order method of multiple scale is proposed by this Roman and Button. So there are two higher order method of multiple scales actually you can use to. Okay, so in the first case, the normal or classical way you can do that thing, so which is available in the book of Nape and Mook, and the second one proposed by this Roman and Button. So in higher order method of multiple scale proposed by Roman and Button, so okay. Roman and Button, number of terms used are less than that of the standard method of multiple scale. So here actually we are not considering some terms similar to that of the standard method of multiple scale. Okay, so this is correct. So because, so when you are solving this order of epsilon square, so we are not considering the term which are present in the secular term of order of epsilon. So in that way some of the terms have been deleted. So in the higher order method of multiple scale proposed by Roman and Button, so we have less number of terms than that present in standard method of multiple scale. So this option is correct. Then in higher order method of multiple scale proposed by Roman and Button, number of terms used are more. So it is not more, so it is less. This option is not correct. The third option and fourth options are, let us see. So in the proposed method of, okay, so one question is there. Chandan has written, what is the value of A0 at t equal to 0 in the last problem? Last problem means, so okay, you go back. So here, so you just see you are going to find this steady state. As you are going to find the steady state, you can take, so already it is written, take A0 equal to 0.1. So you have to take A0 equal to 0.1, but even if you are not taking it 0.1, as you can increase the time and you can see that you are reaching a steady state. So as you are reaching the steady state, the value will be constant. So for more value of time you can actually get this value 0.0922, but in this case we have taken this initial condition A0 equal to 0.1. You can go to the previous slide. Previous. So another problem was there. Go to previous one. No, no, no. So okay, so this question most probably you are asking. So here also you can take a initial condition. Okay, a here also you can take a equal to 0.1 also, but you just try with okay, so he is asking regarding question number 7. Okay, good. So here also you can take a equal to 0.1, but you just see, you just take a equal to, today you take a equal to 0.1 and solve it. Again you just take a equal to, let for example you take 0.001. You can see at steady state actually, so the value will be same. One may take more time to reach the steady state, other may take slightly less time, but in both the cases whatever initial conditions you are taking, so it will reach to this point 0.0363. I hope you got the answer. So here you take any value. So but I have done the simulation with a equal to 0.1. So you can take the simulation with 0.001 or 0.5 also, 0.05 also. You take different value of a0, take different value of a0 and arrive this a value. Okay, so you can find the same thing. Next. Okay, any other question you have? I hope you got it. Next. So if you have any other question in this assignment, so you can ask me. Otherwise, I'll go to the next assignment. I hope you don't have more question in this assignment. Okay, next. So let us see this assignment number 5. Okay. So which of the following statement is incorrect regarding the given equation u double dot plus 4u plus 0.2 u dot plus 0.1 u cube equal to 0. So which is incorrect? You just see, so this clearly this is a Doppling equation. Chandan Pradhan, okay. So this is Doppling equation for free vibration. So I hope you know that this is Doppling equation. So there is no ambiguity here. So you have a equation with cubic nonlinearity, and you just see as you have a plus sign, so you have a hardening type of effect here. So these points should be clear to you when it is hardening and when it is softening. So as you have this point plus 0.1, so then this is hardening effect. The system is having hardening effect, so this is also correct. So it can be converted to fuzzy Doppling equation by taking uncertainty in the initial conditions also. So this is also correct. So you can convert this thing into fuzzy Doppling equation. So you can, for example, so you can this u, that variable u, you can take this as a fuzzy variable also. So I hope by this time you must be knowing what is this fuzzy variable. So here you can take the different membership functions, and you can convert this Doppling equation to a fuzzy Doppling equation. So this variable can be written in a fuzzy way. That means, for example, you want to control the temperature of this room. So you can write that the temperature should be below 25 degree. So in that case you are specifying the temperature that is 25, but instead of specifying that temperature 25, so if you can tell it should be cold, and that cold you are defining between 20 to 25. So in that case you are having a range of range for that variable. So in that case that variable will be converted to a fuzzy variable, and so this equation can be, so you can convert this u to that of a fuzzy Doppling equation by taking uncertainty in the initial condition. So you take some uncertainty in the initial condition and you can solve it and find it. So the system will have an unbounded solution? No. So this system has a bounded solution. So this, due to this thing, this is not correct. So already you have seen, so in case of a Doppling equation with hardening effect, so the response curve we have already plotted. So the response plot will be similar to this. So this is your A versus, so this is your A versus sigma you can put, or omega you can put. So this is the frequency, and this is frequency response plot. So generally you can have a pitchfork type of bifurcation here, and supercritical pitch for bifurcation here, and subcritical pitch for bifurcation here, and a saddle node bifurcation at this point. Next. So which of the following statement is incorrect? So let us see this. Okay, the solution of nonlinear equation can be considered by taking the solution of the corresponding linear equation with a time varying coefficient. So this thing is your method of averaging you used to do this thing. So this is correct. So solution of one nonlinear system can't be extended to another nonlinear system as the superposition rule is not valid for nonlinear system. So this is also correct. So superposition, you cannot apply superposition rule to the nonlinear system because by slightly varying your system parameters, so you may have different type of resonance conditions. So for different resonance condition, your response will be different. So for that purpose, this option B is also correct. So you cannot extend the solution of one nonlinear system to another. So as the superposition rule is not applicable here. So ordering is not important. Ordering is not important while using method of multiple scale. So this option is incorrect. So ordering is very, very important. So if you are instead, for example, instead of putting order of epsilon, so if you are not putting that order of epsilon, then your equation will be different. So in that case, so you may get a wrong result. So for a weak nonlinear system, you can take the equation for that of a strong nonlinear, and your resonance conditions will be different. So that's why, so this is not correct. So Doppling equation may result in fixed point, periodic, chaotic responses depending on the coefficient of the equation and also initial conditions. This is correct. So because you have seen, so for some value of the Doppling equation, so for some coefficient we are getting fixed point. Already I have plotted that fixed point response. So you have seen, so this way this hardening and softening type of things what you have seen. So here we are getting this. So these are the fixed point response. So for example, so if you are writing this Doppling equation u double dot, so instead of plus u, let you put minus u plus epsilon u dot plus or equal to epsilon or plus epsilon u cube equal to f sine omega t. So in this case you can see you have a negative in u. So in this case generally either you can get a periodic response or the response may be chaotic depending on the coefficients. For different value, different coefficients, actually you can get this periodic or chaotic response. So these things you can follow from the lecture notes what we have in the slides what I have shown you in the lectures. Okay, so then this option is only the incorrect option and others are the correct option. Next. So consider two Doppling equations. So u double dot plus 4u plus 0.2 u dot plus 0.1 u cube equal to 0.2 sine omega t, and the second equation becomes u double dot plus 4u plus 0.2 u dot plus 0.1 u cube. So you just see left hand side it is both the cases it is same, but right hand side in the first case it is 0.2 sine omega t, and in the second case it is 4 sine omega t. Okay, so as it is 4 sine omega t, you just see, so this is strong forcing we have, and in this case in comparison to this 4, so this term is 0.2, so this is weak nonlinear term, weak forcing. So you have a weak forcing in case of 1, and in case of 2 you have a strong forcing. So in case of weak forcing, so you can have actually this so you can have the simple resonance condition, and in case of the strong nonlinear system, so you can in addition to your this prime resonance or the simple resonance condition, so you can have superharmonic and subharmonic resonance conditions. So let us see in this case, in the first system resonance will occur when omega equal to 0.2 radian per second. So you just see omega, so here omega equal to, so this is omega square equal to 4, so omega equal to 2, in both the cases omega equal to 2. So here when this omega will be equal to 2, then only you can have the resonance condition, that is your primary resonance condition or simple resonance condition. So this option is not correct. So in the second system, the resonance will occur when the external frequency is 1 radian. So you just see when it is equal to 1 radian, so it will not have any of these three, because you have a cubic nonlinear system. So as you have a cubic nonlinear system, so resonance will occur when the external frequency omega will be equal to, so here your omega n equal to 2, so you can have the superharmonic resonance condition, subharmonic resonance condition and primary resonance condition or simple resonance condition. So one condition will be at omega equal to 2, the second condition will be at 2 by 3, and the third condition will be equal to 2 into 3, that is 6. So in 6, so here your omega n is greater than this thing, this is your subharmonic resonance condition and this is your superharmonic resonance condition. So you have these three resonance condition here. So in the first system, so this option is not correct as we have this 1. So 1 is not correct. So at 2 you have a resonance condition and 6 also you have a resonance condition, but at 1 you don't have any resonance condition because you have a cubic nonlinearity. So if you have a quadratic nonlinearity, actually you can have a resonance condition at 1 also. So in the first system, the resonance will occur when omega equal to 5 radian per second. So this is not correct. So 5, there will be no resonance condition. So in the third case, option D. So in the second system, this is the second system, the resonance will occur when the external frequency equal to 2. So yes, at 2 radian per second you will get, omega equal to 2/3 you will get, and omega equal to 6 radian also you will get. So that's why the option D is correct. Okay, so next. So consider the Doppling equation with u double dot plus 4u plus 0.2 mu u dot equal to plus 0.1 k u cube equal to 0.2 sine omega t, where mu and k are constant. So which of the following statement is wrong? So here statement we have to see which is wrong. So others will be correct and this is wrong. With increase in mu for constant value of k, the response amplitude will decrease. So definitely with increase in mu, as you have a positive here, positive damping here, so if you are going on increasing mu's, that damping will be increased. As damping is increased, the response amplitude definitely it should decrease. So with positive value of k, so you just see with positive value of k, so this will be hardening type of effect will be there. With positive value of k at omega equal to 2, so you just see omega equal to 2, so that is the primary resonance condition. So omega equal to 2, the response amplitude is maximum, so the response amplitude will be maximum. Okay, so for omega equal to, actually response amplitude may be, okay, so it can increase also. So generally it reach the maximum value, or it can, okay, so you can see, so at this option is also the with positive value of k at omega equal to 2, the response amplitude, so this is not also not properly correct actually. So it will have a maximum value away from 2 also, to the right of 2. So for omega, okay, so for omega equal to 2, the response amplitude increases with increase in k value from 0.2 to 0.4. So yes, with increase in the response amplitude will increase, this is correct. So you can plot different value with different value of k, so you can plot the response. Okay, so with the different value of k, if you plot the response, it will be like this. So for omega less than, very less than 2, the response amplitude tend to 0. Okay, so actually this is wrong. This is wrong, I told you. So because, so it will be maximum, so when it is away from 2 also. So when it is away from 2, it will reach the maximum. At 2, it will not reach the maximum. So in case of actually undamped, in case of undamped system, linear undamped system, so you have seen, so the response will be like this. So in this case only, so it is maximum at omega equal to 2. Omega equal to 2, so the response amplitude A tends to infinite. So A tends to infinite at omega equal to omega n. But for nonlinear system, as it is bending towards right or left, depending on you have the softening or hardening effect, so the maximum will not occur at omega equal to 2, but away towards right in the case of if it is so if it is a hardening type of response, and if it is softening type of response, then towards left it will be maximum. So for omega very less than 2, the response amplitude tends to 0. You just see very less, so this is 0, so this is also 0 this side, so this is also correct. So these three options are correct and this option is not correct. Okay, next. So consider the Doppling equation u double dot plus u equal to 0.2 mu u dot plus 0.1 ku equal to 0.1 f sin omega t, taking value k equal to f equal to 1, mu equal to 0.1 and epsilon equal to 0.1. The value of determining parameter sigma for a equal to 1 are these and these. So you can solve this equation and you can find it. Okay, so this problem you can solve. So or you can, some hints is given, so this is the solution equation you can get by method of, by applying method of, okay, so by method of averaging you can use, or by method of multiple scales also you use. So you can find this equation. After getting this equation, you write a code. Okay, so 2-line code you can write in MATLAB, and by substituting this value you can find different value of a. So for a particular value of sigma you can find particular value of a. So the value of determining parameter sigma for a equal to 1. So you substitute a equal to 1 in this equation and other values are given. So you can find actually 2 value of this is root over. So you can find 2 value of this sigma. So these are sigma. Okay, next. Consider Doppling equation u double dot plus 9u plus 0.2 u square plus 0.1 k u cube equal to 0. So using LP method, that is Lindstedt-Poincare method, one may use the following formula to find the frequency response plot. So the formula is given to you. So now you can check which of the statement is correct. So for k equal to 1, omega is less than the linear natural frequency of the system. So you can verify that this is the correct option. Okay, next. Which of the following statement is true? So in primary resonance for system with, okay, so there is some more question, Chandan Pradhan. So what is the value of alpha? Okay, so which question? Okay, in question number 5, you go back. Okay, so what is the value of so you just see what is the value of alpha. So alpha is this one. You just see what you are using the alpha, it depends on that thing. So you just see one can put this alpha, if you are writing alpha as the coefficient of u cube. So here in this case this is equal to 0.1 k. So this is equal to alpha and this 0.1 is there, and so in that case k is given to be 1, so this is equal to alpha equal to 0.1. Okay, so if you are using actually epsilon you are using, so as you are writing epsilon, so you just see, let me write in using this epsilon. So now your this epsilon alpha cumulative, write using this epsilon alpha u cube. So in that case you just see this is equal to 0.1 into 1 u cube. So this is equal to 0.1 u cube. So so your epsilon is taken to be 0.1. So then this is equal to 0.1 into 1 u cube. So you just see, so this is the value of alpha. So alpha equal to 1. So I hope you understood this thing. Is it okay? So You just take the term, substitute the value of epsilon, epsilon is given and k is also given. So from that coefficient, so you can find what is the alpha. You just see this alpha and coefficient of u, so they are of the same order. So that is also equal to 1. So that's why, so this alpha you have taken it equal to 1. So you can use any of the method of multiple scales also you can use and you can find the answer. Okay, next. So already we have discussed this part, I think. Okay, so we are discussing this question number 7. So which of the following statement is true? So in primary resonance for the system with Doppling equation having weak forcing, the transient response amplitude tend to 0 in the presence of positive damping. In primary resonance for the system with Doppling equation having weak forcing, so the forcing is weak, the transient response amplitude tends to 0 in the presence of positive damping. Okay, so in primary resonance for the system with Doppling equation having strong forcing, the free vibration amplitude tends to 0. The free vibration amplitude tends to 0 in the presence of positive damping. So when the response, when the frequency of the excitation is away from the resonance condition, the transient response amplitude tend to 0 in the presence of positive damping. So for superharmonic resonance condition, the transient response amplitude never tend to 0 in the presence of positive damping. Actually, so this option is correct. So in superharmonic resonance condition, what is transient response? Transient response, so you have two type of response. So one is your transient response and other one is the steady state response. As t tends to infinite, the response what you are getting, so that is the steady state response. And in case of the transient response, for example, you just take e to the power minus I omega nt. So in this case, exponentially this term exponentially will decrease. So very quickly, so it will comes to 0. So as very quickly it comes to 0, so this transient response, so it will die down. So generally minus epsilon mu t, let me put. So mu is your damping. So if you actually put the damping value, so some value of positive damping, then the response if you plot, as this is exponential function, so exponentially it will decrease and it will come to 0. But in case of the superharmonic resonance condition, so you can check that this is never comes to 0 and sometimes you will have a non-zero term. So you will have a non-zero term. So due to the presence of non-zero term, so this response amplitude will never be 0 in the presence of a positive damping. Though the damping will be there, but the response will not be 0. Okay, next. Which of the following statement is wrong? For the system with quadratic damping, the response amplitude decreases algebraically. You can note it, so it decreases algebraically. This is correct. For system with linear viscous damping, already you know, so it decreases exponentially. This is also correct. So for the system with Coulomb damping, the response amplitude decreases. So this is not correct. Actually, this decreases like this. So it decreases what? So it decreases not exponentially or algebraically. So it decreases like this. For van der Pol oscillator, the response amplitude leads to limit cycles. So this is also correct. So this part is not correct. So you can plot yourself for the Coulomb damping and visualize how the response amplitude is decreasing. So for the system, question number 9. So for a system given by dx by dt equal to y and dy by dt equal to minus 9x, the equilibrium point. So you can find the equilibrium point. You can find the equilibrium point by substituting dx by dt equal to 0 and dy by dt equal to 0. So if you substitute dx by dt equal to 0, so you got y equal to 0. And similarly here you got minus 9x equal to 0 by substituting dy by dt equal to 0. So minus 9x equal to 0. So 0, 0 is a solution. So 0, 0 is the equilibrium point. So the equilibrium point 0, 0. So now you can find what is this equilibrium point, whether this is saddle point, stable node, stable spiral or center. So you can check it. So how to check it? So you just find the Jacobian matrix. So find the eigenvalue of the Jacobian matrix. So what is Jacobian matrix? So your first equation, x dot equal to y. So if you write the Jacobian matrix, so it will be equal to, so you just see, so this equation, so x term is 0, so there is no x term here, and so this is 0, and the y term, so dy, so if you differentiate this with respect to y, so this becomes 1. Similarly for the second equation, so you have a x term is there, so if you differentiate with respect to x, this becomes minus 9, and as there is no y, so this becomes 0. So this is the Jacobian matrix. So now j minus lambda I you just make. So if you make j minus lambda I determinant equal to 0, so you can write this thing equal to, so this is minus lambda, so then this is 1, then this is minus 9, and this is minus lambda. So this equation becomes lambda square minus 9 equal to 0. So lambda square minus, so this is, or plus 9. So minus 9 into 1, this is minus 9. So minus minus plus 9. So this is equal to 0. So lambda square equal to minus 9. So now you got lambda equal to plus minus 3i. So you got this plus minus 3i. As you are getting plus minus 3i, so what is the solution? So you can see the real part is 0 and you have imaginary part 3i. So in that case you will get only sine and cosine and you will get it center. Next. So for a dynamic system, okay, so for a dynamic system given by x dot equal to y and y dot equal to 4x, for the equilibrium point 0, 0, the trace and determinant of the Jacobian matrix are respectively. So you just find this is straightforward equation and you can find, so you are getting this is equal to 0 and minus 4. So you can write down the Jacobian matrix also. So from that thing you can find, so what is the Jacobian matrix in this case? Jacobian matrix equal to, so if you differentiate with respect to x, this is equal to 0, with respect to y this is equal to 1, and with respect to, for the second equation, with respect to x this is equal to 4, with respect to y this is equal to 0. So this is the Jacobian matrix and you can find the trace and determinant of this one and you can find it. Okay, next. So we'll stop it here because, okay, so next class now it is time. So we'll discuss this assignment 6, 7 and other assignments. So on 5th, and if you have no problem, so then we can have one more session also and we can discuss all the assignments. Okay, so if you have any other question then you can ask. Okay, so as you don't have more question, you can see if there is any other question. I don't think there is any question. Okay. So can you provide MATLAB code for constructing frequency response and amplitude response curve for Doppling equation? So you just see, so in case of Doppling equation, you are getting a quadratic equation only. So for quadratic, so already, can you go back? So one equation already I have written, that quadratic equation sigma equal to, go back. So this is the equation you just see. So for Doppling equation, this equation you can plot sigma equal to 3 by 8 alpha by omega 0 a square plus minus k square by 4 omega 0 square a square minus mu square half. So you have two value. So for plus value you have sigma 1, for minus value you have sigma 2. So you have two sigma value. So now what you do? So you just write a code, 2-line code. Let me write. So take a equal to, for example, take a with increment 0.01. So let it take up to 10 or 20. You just let it take up to 15. Then you just write the sigma equal to sigma 1 SIG1 equal to this equation you just write. So this is equal to 3 by 8 into alpha ALPHA, you just write alpha for alpha, then omega 0 OM0 you just write. So into a square, so a is there, so you can put a dot square. So this is the thing you have to write. Okay, so a square if you write then it will be wrong, so you have to put a dot square. Okay, so this way you just put the symbol, then you will get it. So a square plus, then the other part is simple, so other part that is k square, so k square, k or k square, this way you write, by, so this part you can write 4 omega 0 square, also you can write into, for a square you have to write a dot square, so this way you just write minus mu square. So you just define different value of mu, so this is sigma 1. Okay, sigma 1 will be square root of this thing sqrt, so this is here, so this is the term, so you just write sqrt, this thing sigma 1, then sigma 2 you got. Similarly you write this equation sigma 2 you got, then you just use the command plot sig 1 comma a, then hold on, plot sig 2 comma a. So these two plot, just to plot this thing, then you will get this curve. So Doppling equation, it is very simple, but if you have more number of terms, so you have more equations, when you have 4 equations, 5 equations, that time you have to use the Newton's method. Here you need not have to use the Newton's method to solve this equation to find. So here this is very straightforward, you just use this equation, and for Doppling equation you can plot. Okay, I hope you understand this thing. So if you have any other query, then you can ask. So Jai Krishna. Okay, so thank you. So thank you all of you. So with this thing, let us close this session here. And okay, so you plot yourself, all of you plot and send me your code. So if you have any box, then I can correct it. But I want you to try. So without trying, if you want just the code, then you will not learn. So I want you just write down the code. So if you are finding any difficulty, then I will correct it. But if you will not try, then you will not learn. Okay, so with this thing, let me thank you, and we'll next meet on 5th April at same time at 4:15 p.m. So thank you very much.